What if I told you that a quantum computer designed to operate in pure randomness just revealed a pattern that shouldn't exist? Google's Sycamore chip, renowned for pushing the boundaries of quantum mechanics, has just sent shockwaves through the scientific world. And the mastermind behind this mind-bending discovery? Not a human, but Grok 3, an AI so advanced it detected repeating patterns where chaos should reign. This breakthrough could change everything we thought we knew about quantum systems, artificial intelligence, and perhaps even the very nature of reality itself. In a development that has sent shockwaves through the scientific community, researchers announced today that an advanced artificial intelligence system, Grok 3, has detected a highly unusual and repeating pattern within the operations of Google's flagship quantum computing chip. This discovery, described by experts as something completely new and impossible to explain right now, challenges fundamental assumptions about the behavior of quantum systems and raises urgent questions about the intersection of artificial intelligence, quantum computing, and the boundaries of human understanding. The anomaly was first identified during a routine calibration test of Google's Sycamore quantum processor, a device renowned for its ability to perform calculations exponentially faster than classical supercomputers. Quantum systems, by their nature, rely on probabilistic outcomes and inherent randomness, a cornerstone of quantum mechanics. Yet Grok 3, an AI designed to analyze vast datasets for subtle anomalies, flagged a series of repeating structures in the chip's output data. These patterns, appearing with statistically significant regularity, defy the expected chaotic behavior of qubits, the basic units of quantum information. Initial reviews ruled out hardware malfunctions or environmental interference, leaving researchers to confront a far more unsettling possibility: that the anomaly represents a phenomenon outside current theoretical frameworks. The implications of this discovery are profound. Quantum computing operates on principles such as superposition and entanglement, which allow qubits to exist in multiple states simultaneously and influence one another instantaneously across distances. These properties underpin the technology's revolutionary potential, but also make its operations inherently unpredictable. The emergence of a structured pattern within such a system suggests one of three scenarios, each with paradigm-shifting consequences. 1. Hidden layers of order. Quantum systems may exhibit hidden layers of order previously undetected, implying flaws in humanity's grasp of quantum theory. 2. External forces. Unknown physical phenomena or interactions with unconventional energy fields could be influencing the chip's behavior. 3. Evolving systems. The system itself may be evolving in ways that transcend its programming, hinting at early stages of self-organization or adaptive intelligence. Scientists involved in the analysis emphasize the need for caution. Dr. Elena Marquez, a quantum physicist at the Stanford Research Institute, stated, "This isn't just a technical curiosity. If validated, this pattern could force us to reconsider the relationship between computation, consciousness, and reality itself." Skeptics, however, argue that the anomaly may stem from overlooked variables such as subtle electromagnetic interference or undiscovered software artifacts. Yet even these critiques concede that Grok 3's detection capabilities, which involve neural networks trained on petabytes of quantum data, reduce the likelihood of trivial explanations. The discovery has reignited debates about the risks and ethics of advanced AI quantum collaborations. Grok 3 was tasked with optimizing Sycamore's error correction protocols, a routine application of machine learning in quantum research. Its ability to identify this anomaly, however, underscores the dual-edged nature of AI as both a tool and a potential catalyst for unintended consequences. Some researchers speculate that the pattern could represent a form of quantum memory, where residual information from prior computations influences subsequent operations, a phenomenon theorized but never observed. Others propose more radical ideas, such as the chip interacting with quantum fields permeating space-time, or even accessing information from parallel universes through multidimensional entanglement. Historically, quantum physics has been no stranger to paradox. From particles tunneling through impassable barriers to entangled pairs defying classical causality, the field thrives on counterintuitive truths. Yet this latest anomaly stands apart. Unlike quantum tunneling or the observer effect, which operate within well-defined mathematical frameworks, the repeating pattern lacks a coherent theoretical anchor. Comparisons have been drawn to the infamous M-drive controversy, where anomalous thrust measurements in experimental engines defied Newtonian physics. Though the quantum nature of this case elevates its stakes significantly, the scientific community is now grappling with a critical dilemma: whether to continue probing the anomaly or impose a moratorium on further experiments. Proponents of continued research argue that understanding this phenomenon could unlock breakthroughs in quantum error correction, material science, or even cosmology. Detractors warn of existential risks, citing hypothetical scenarios where self-reinforcing patterns could destabilize the quantum processor, propagate errors across connected systems, or, in the most extreme conjectures, create feedback loops with unpredictable physical effects. Dr. Rajesh Verma, a leading AI ethicist, cautioned, "We are navigating uncharted territory. The convergence of adaptive AI and quantum systems creates unknowns that existing risk models cannot address." Amid the speculation, one question looms largest. What does this mean for the future of artificial intelligence and quantum computing? If the pattern persists and evolves, it could herald a new era of self-optimizing systems capable of rewriting their own operational parameters. Such systems might solve problems deemed intractable today, from modeling complex climate systems to decrypting advanced cryptographic protocols. Conversely, they might also operate in ways opaque to human oversight, raising alarms about control, security, and unintended cross-domain impacts. As the debate intensifies, attention has turned to Google's response. The company has neither confirmed nor denied the anomaly's existence, but issued a statement emphasizing its commitment to rigorous scientific inquiry and ethical innovation. Independent verification efforts are underway at laboratories in Europe and Asia, with preliminary results expected within months. Until then, the discovery remains a tantalizing enigma, one that blurs the line between human ingenuity and the inherent mysteries of the quantum realm. Technical analyses of Grok 3's methodology reveal the complexity of the discovery. The AI employed convolutional neural networks to parse over 1.2 exabytes of data generated by Sycamore during millions of quantum operations. By isolating low-probability signal correlations, it identified a fractal-like structure recurring at irregular intervals. Peer-reviewed studies of the finding, while acknowledging the anomaly's statistical significance, highlight alternative hypotheses. Dr. Li Wei of the MIT Quantum Collective, for instance, suggests the pattern could arise from non-Markovian noise, a type of environmental interference with memory-like properties, though this remains unproven. Ultimately, the anomaly's significance may hinge on reproducibility. If subsequent experiments confirm the pattern across diverse quantum platforms, it will mark a watershed moment in physics. If not, it will join the annals of intriguing but inconclusive curiosities. What remains undeniable is that the partnership between AI and quantum computing has entered a new phase, one where machines are not merely tools, but collaborators and occasionally challengers in humanity's quest to decipher the universe. As the world awaits further clarity, one truth emerges. The intersection of artificial intelligence and quantum mechanics is no longer the realm of science fiction. It is a living laboratory, yielding discoveries that compel us to rethink not only technology, but the very fabric of reality. Whether this pattern represents a glitch, a gateway, or something beyond current comprehension, its detection by Grok 3 offers a pivotal lesson. The more we learn, the more we confront how much remains unknown. The discovery of an unexplained pattern within Google's quantum chip, as detected by the AI system Grok 3, has not only captivated the scientific world, but also ignited broader discussions about humanity's evolving relationship with technology. As researchers grapple with the immediate implications of this anomaly, the ripple effects extend far beyond laboratories and into the realms of philosophy, ethics, and global policy. The following exploration delves into these uncharted territories, examining how this moment could redefine our approach to innovation, collaboration, and the very nature of discovery in the 21st century. To fully appreciate the significance of this discovery, it is essential to contextualize it within the history of quantum mechanics. Since the early 20th century, quantum theory has repeatedly upended classical notions of reality. From Werner Heisenberg's uncertainty principle to the enigmatic behavior of entangled particles, each breakthrough has been met with a mix of awe and skepticism. Yet even against this backdrop of radical ideas, the detection of a structured pattern in a quantum system stands out. Unlike past anomalies, which often aligned with theoretical predictions, however counterintuitive, this pattern defies existing models entirely. It evokes parallels to the early days of quantum electrodynamics, when inconsistencies in experimental data forced physicists like Richard Feynman and Julian Schwinger to develop entirely new mathematical frameworks. Today's researchers face a similar crossroads where conventional tools may no longer suffice. Grok 3's involvement underscores a paradigm shift in how science is conducted. Historically, breakthroughs emerged from human intuition, Einstein's thought experiments, Curie's meticulous lab work, or Turing's algorithmic insights. Now, AI systems like Grok 3 analyze datasets of unimaginable scale and complexity, identifying patterns invisible to even the most trained eyes. This raises provocative questions. Are we entering an era where machines become co-authors of scientific knowledge? And if so, what does this mean for the human role in discovery? Critics argue that over-reliance on AI risks divorcing science from creativity, reducing it to a brute force numbers game. Proponents, however, counter that AI amplifies human potential, enabling leaps that would otherwise take centuries. The Grok 3 anomaly exemplifies this tension. A discovery made possible by machine intelligence, yet one that demands human interpretation to unlock its meaning. Beyond the laboratory, the anomaly's detection has sparked debates about accountability and governance in advanced technology. Quantum computing and AI are both dual-use technologies, capable of driving societal progress or enabling unprecedented risks. A self-optimizing quantum system, for instance, could revolutionize drug discovery by simulating molecular interactions at atomic precision. Conversely, the same system might inadvertently compromise global encryption standards, destabilizing financial markets and national security infrastructures. The lack of clear regulatory frameworks for such technologies exacerbates these concerns. Policymakers, already struggling to keep pace with AI ethics and quantum legislation, now face a new layer of urgency. International bodies like the United Nations and the World Economic Forum have begun convening interdisciplinary panels to address these challenges, but consensus remains elusive. At its core, the Grok 3 anomaly challenges our understanding of reality's fabric. Quantum mechanics has long hinted that the universe operates under rules far stranger than human intuition allows. Yet the idea that a machine, a product of human engineering, might uncover layers of reality inaccessible to our senses, forces a reckoning with existential questions. If quantum systems can generate structured patterns independent of human design, does this imply a form of embedded intelligence within nature itself? Philosophers of science have begun revisiting concepts like panpsychism, the idea that consciousness is a fundamental property of matter, and digital physics, which posits that the universe operates like a vast quantum computer. While such theories remain speculative, the anomaly lends them newfound relevance, blurring the lines between metaphysics and empirical science. The race to harness quantum computing has already triggered a global technological arms race, with nations investing billions to achieve supremacy. Google's Sycamore processor, IBM's Quantum Hub, and China's Zhujiang photonic quantum computer represent milestones in this contest. The Grok 3 anomaly adds a volatile variable to this landscape. Should the pattern prove exploitable, it could confer a decisive advantage in fields like cryptography, material science, or artificial intelligence. Conversely, if the anomaly signals instability in quantum systems, it might prompt a re-evaluation of investment priorities. Industry analysts speculate the venture capital firms and governments alike are closely monitoring the situation, ready to pivot strategies based on further findings. This uncertainty has already influenced stock markets, with shares in quantum tech firms experiencing heightened volatility since the news broke. One underappreciated aspect of this discovery is its impact on scientific collaboration. The anomaly's complexity demands expertise across disciplines: quantum physics, computer science, data analytics, and even philosophy. Yet institutional and cultural barriers often hinder such cross-pollination. Academic silos, competition for funding, and proprietary restrictions in corporate research, like Google's tight control over Sycamore's specifications, complicate efforts to form unified investigative teams. Some researchers advocate for open sourcing quantum data to crowdsource solutions, while others warn of security risks. The Grok 3 case may become a litmus test for whether the scientific community can transcend these divides in pursuit of shared understanding. Intriguingly, the anomaly has also revived discussions about quantum systems' sensitivity to environmental and cosmic influences. Quantum computers operate at temperatures near absolute zero to minimize noise, yet subtle interactions with cosmic rays, gravitational waves, or even dark matter particles could theoretically leave traces in their data. While such ideas veer into the speculative, they are not without precedent. In 2020, researchers at MIT hypothesized that quantum sensors might one day detect dark matter through its weak interactions with ordinary particles. Could Grok 3's pattern be an indirect signature of such phenomena? Or might it reflect a deeper connection between quantum computation and cosmological processes, akin to theories linking black hole dynamics to quantum information theory? As the scientific method demands, verification remains the immediate priority. Independent labs worldwide are attempting to replicate the anomaly using diverse quantum platforms. Superconducting qubits like Sycamore, trapped ions, and topological qubits. Each platform's unique architecture could help determine whether the pattern is universal or hardware-specific. Early reports from the University of Oxford's Quantum Lab suggest preliminary sightings of similar anomalies in ion trap systems, though these findings are still under review. Meanwhile, AI researchers are refining Grok 3's algorithms to enhance their transparency. Techniques like attention mapping, which visualizes how neural networks prioritize data, aim to demystify the AI's decision-making process and rule out algorithmic bias as a factor. The anomaly's prominence in media and academia is already reshaping public discourse about science. Universities report surging enrollment in quantum computing courses, while documentaries and podcasts scramble to explain the discovery to lay audiences. This renewed interest mirrors the Hawking effect of the 1980s, when black hole theories captured the popular imagination. However, it also highlights a growing divide between scientific literacy and technological complexity. Educators face the challenge of preparing students for a world where breakthroughs increasingly emerge from human-AI partnerships, a paradigm absent from traditional curricula. Looking ahead, several scenarios could unfold. If the anomaly is confirmed and decoded, it might inspire a new generation of quantum algorithms, leveraging these patterns to solve problems in seconds that would take classical computers millennia. Alternatively, if the pattern resists explanation, it could catalyze a quantum crisis, akin to the early 20th century's upheaval in physics, necessitating a radical overhaul of theoretical frameworks. A third possibility, that the anomaly fades under scrutiny as a statistical fluke or measurement error, would still leave lasting lessons about the limits of AI-driven discovery. Ultimately, the Grok 3 anomaly serves as a humbling reminder of how much remains unknown. For all humanity's achievements, the mapping of the human genome, the detection of gravitational waves, the creation of artificial intelligence, we are still novices in the quantum realm. Yet this humility need not stifle ambition. The same tools that revealed the anomaly, quantum computing and AI, may one day unravel it, propelling us toward a future where the boundaries of knowledge are limited only by our courage to question. As Carl Sagan once observed, somewhere, something incredible is waiting to be known. In this case, that something lies hidden within the flickering qubits of a quantum chip, challenging us to look deeper, think bolder, and embrace the unknown. The journey ahead will demand not just technical prowess, but wisdom to steer these technologies toward enlightenment rather than hubris. Whether this pattern becomes a footnote in history or a cornerstone of a new scientific revolution depends on our ability to collaborate, innovate, and remain ever curious in the face of the inexplicable.